Okay, so how many have heard of a sequence before? The term a sequence. Okay, Jacob has, and Sean, and many of you. So it's a sequence of events, right? Sequence of events. Well, in math, a sequence is actually a list of numbers in a definite order. So let me go ahead here and hold on here. I don't want to go that far. Wait. Okay, let me just go down here. Okay, so a sequence can be thought of as a list of numbers written in a definite order. Okay, a definite order. And traditionally, the sequence of numbers follows some kind of pattern. Okay. The number a sub 1 is called your first term. The number a sub 2, whatever it is called your second term. And the number a sub n is called your nth term or your general term. Okay. So the sequences keep going and going and going. They go on to infinity. And the n, of course, is an integer. And let me just, I don't want to get too technical here, but this is notation for a sequence. Okay, this is a standard notation. The sequence of numbers is put in brackets, and you can denote that sequence as you see there. The sequence of numbers. Okay. So let me show you some examples of sequences. Okay, let me show you some examples. Okay. I'll highlight this just because. Now they comment here that this is example 1 actually. Some sequences can be defined by giving a formula for the nth term. Okay, so some sequences, well, pretty much all sequences have some kind of pattern to them, but sometimes the sequence you can put a formula. Okay, so in the following examples, we give 3 descriptions of the sequence. Okay, 3 descriptions. So you see there like an A. You see here an A. Maybe I can highlight this. Hold on one moment. Yeah. So these are 3 ways to notate a sequence. So this sequence, the pattern, the numbers, this is the sequence in A. It goes a half. So the sequence starts at a half, then it goes 2/3, 3/4, 4/5, and the pattern for the sequence is n over n plus 1. And so that, like the sequence, you can represent it as a list, as you see on the right there. This is the A, part A here. And then, let me just see here, one moment. Don't like that being blocked particularly. Let me see if I can. Yeah. But it's, all right, highlighting all. All right, hold on, everybody. Yeah, I'll just have to leave it like this. So these are just 3 ways to denote a sequence. And sequences usually start at n equals 1, but a sequence doesn't have to start at n equals 1. Okay. But for our purposes, our sequences will normally start at n equals 1. So I think it would be good to just do a few examples here. Let me bring up the examples here. to kind of get you started here. Okay, so what we're going to do is we have these three sequences, and we want to find formulas for them. Let me give you a moment to copy the example down. Okay, so let's look at this first sequence here. Let's look at this first sequence. So for that first sequence, what's the first term? I mean, in other words, and I'm gonna actually hold on here. Let me just get this thing here. All right. So if we look at the first sequence here, first term is a half. Second term is 2/3. Third term is 3/4. And oftentimes it helps to look at the term of the sequence and then what's going on the right. Okay, so oftentimes you can relate the term of the sequence to the term on the right. Because what we want when they say give formulas for the following sequences, of course, what we want to know is what's the formula for the nth term in the sequence. What's the formula for the nth term in the sequence? What do you think it would be here? Samuel? Tal, what do you think?
I think for A, would it be n over n plus 1?
N over n plus 1. Yes, good, Tal. And I'm assuming Samuel agrees. Yes, excellent, excellent. I mean, are there any questions on that? Well, all right, let's do this. So we're just kind of talking right now. We're talking right now, and then I'm going to formally show the work, the worked out part. But we're just kind of having conversation. Are there any questions on that for part A? Naturally, we start off with an easy one, right? All right, well, let's go to part B. Let's go to part B. Okay, here's the sequence. And again, I find it very helpful to help me get a formula for the sequence. I find it helpful to write down the terms. The first term, a sub 1, is negative 2/3. Yes, Samuel?
Negative n over 3.
Let's see here. Hold on. Hold that thought. Well, are all the terms negative, though?
No, wait, are we adding or are we multiplying?
No problem. So we got this is what's called an alternating sequence, because some of the terms are positive and some of the terms are negative. Right? So we need to have something in the formula to handle that, so to speak. I mean, what would...
Are we adding these or are we multiplying these?
Well, let me ask you this. What about the denominator? What do you see looking at the denominators here? The 3, the 9, the 27, the 81. What
Factors of 3.
Factors of 3. Okay. 3. What am I going to put here in the denominator? 3. I need more than 3, though. All right, Jacob, I like that. 3 to the power n. Okay. All right, that will handle the denominators. Now, please let me know if you have any questions. Question is now, what about the numerator? Numerators. We have a 2. First term has a 2. Second term has a 3. Third term has a 4. Fourth term has a 5. Samuel? Yep.
N plus 1.
I like that. Okay, we're almost there. N plus 1 over 3 to the nth power. So we've accounted for all the behavior except now we have to account for
the negative.
We got a negative, and then a positive, and then a negative, and then a positive. That's right, Sophie. What do you think, Tal?
I thought I had it, but it didn't. But I think it has something to do with the power of n being negative, because that would be the only thing that.
That's right.
Yeah, the change.
And Leping set it -1 to the nth power. That's right, Leping. Good. So that's right. So you see how we kind of reason this out? We reason it out, and that's going to be the answer. So what I want to do is I want to go to the next page where I have things a little more formally written down, and we will do C, but let me show you the next page, just so I mean, next page has basically what we just discussed. So here are the solutions for A and B. Let me give you a moment to copy those down if you need to. I mean, I think everybody is taking notes, right? It's a good idea. Let's try to get that a little better here. Hold on. Okay, so I'll give you a moment here to copy this down. Are there any questions at all? Who's feeling good? Who's feeling good so far? Okay, wonderful, wonderful. And you see what I did here, by the way. So what I did was when I did these problems, when I worked it out this way, I just kind of I wrote the 2 as 1 plus 1. I wrote the 3 as 1 plus 2. I wrote the 4 here as 1 plus 3. And then I can relate, you know, the 1. Let me put that maybe in blue. I can relate, like I can see, okay, I got a 1 here and I have a 1 here. I have a 2 here and a 2 here. I have a 3 here and a 3 here. So it's something you intuitively do. But, you know, that's what you're intuitively doing to get the pattern. And same kind of thing here. Same kind of thing here. The negative 2/3, that negative can be written as -1 to the first power. And then positive 3/9, well, that's taking -1 and squaring it. Okay, I mean, that would get me a plus, right? Okay, and notice the 2, you know, and the 2, and the 1, and the 1, and then I have a 3 here, and I have a -1 cubed here, and that gets me a -1, a negative. So you see, you just kind of build up each term. You basically dissect the term and until you figure out the pattern. All right. Is this how many find this helpful? That I wrote this out in some detail. Okay, Samuel's liking it. Many people. Okay, good, 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 wonderful. Are there any questions? Okay, well, we have another sequence here to look at. The third one, sequence C. Now, this sequence here looks like it goes 5, 1, 5, 1, 5, 1, 5, 1, 5, 1 on to infinity. It just keeps doing that. So that's certainly an interesting series, and we want to see if we can get a formula for that. Okay. Take a moment and see if you can think of a formula. I mean, well, this one is a difficult one, and I don't know in my years teaching if any students ever been able to get the formula for a sequence like this, like you know, somebody just new to learning it. Okay, sequence keeps going. So think for a moment, and then I'll show you the answer, okay? And you're welcome to chat what you think is the answer out, and I'll let you know if it's a, you know, right or if it's a good try. All right, well, any thoughts? About what the formula is for this sequence C? I bet eventually you would be able to get determine the formula. I bet you would.
I'm not sure exactly how you would word it, but something in the regards of adding 4 and then subtracting 4 and then adding 4 and then subtracting 4, or some kind of thing that would result in doing that, maybe?
Well, indeed, there is a difference of 4 between these values, and that's important to notice, Sophie. That is important to notice. Sean says maybe the cosine of 2 times the cosine of x plus 3. Now that's interesting. So Sean is saying, hey, 3 is halfway between 5 and 1. And let's see, if we go 3 plus 2, we get a 5. If we go 3 minus 2, we get a 1. 3 plus 2 is 5, 3 minus 2 is 1. Sean, the thing is, the cosine of x, I know you're using that to get like a plus or minus, but it won't quite work. But you're on the right track. And Sophie, you're thinking you're on the right track. Samuel?
N plus or minus the square root of 16.
10 plus or minus the square root of 16.
N.
Oh, N. Well, I'm not sure if we did that, and I'll just let me just try that, okay? So, okay, Sean's suggesting this. It might be N plus or minus 4, right? So, indeed, the thing is, you don't know if it's a plus or minus. So you need that. That's also dependent on n. You need like a -1 to the nth power to get the oscillation in there. But I know where you're coming from. I don't think it'll. the problem is like when, like, okay, a sub 1 is like 1 plus 4. That gives you 5. A sub 2 would be, though, 2, then minus 4, and that won't get you the 1. That's the problem. But good try, good try. Let me show you the answer. So you're all headed in the direction here. This is what I did. This is what I did. I made a little picture. Okay, so this is kind of where Sean was coming from. So on the vertical axis, I have a sub n, and on the horizontal axis, I have n. And what I do is I plot the terms. So a sub 1 is equal to 5. So I put a dot here. A sub 2 is equal to 1, so I put a dot here when n is 2. When n is 3, the third term is 5, so put a dot there. And the fourth term is 1, I put a dot there. And so it turns out that the pattern, the general formula, is going to be, you see 3 here, is right down the middle. So you could have, this formula would work actually. A sub n equals 3 plus 2 times negative 1 to the n plus first power. Okay, A sub n is equal to 3 plus 2, but sometimes the 2 is positive, sometimes it's negative, so we put a negative 1, but not to the n power, n plus 1 power. Okay, where n equals 1, 2, and so forth. So like if we use that formula, we got to check to make sure the formula works. A sub 1 would be 3 plus 2 times a negative 1 to the 1 plus 1 power. That's the same as 3 plus 2 times negative 1 squared. Well, that gives you positive 5, so that checks out. A sub 2 would be 3 plus 2 times negative 1 to the 2 plus 1 power. Okay, that'll equal 3 plus 2 times negative 1 to the third. Well, negative 1 to the third is negative 1, so that's going to give you 1. It works out. So this is your formula here. I mean, I guess I boxed it, but I'll circle this. Okay, and there are other. You could get this sequence with another formula as well. This isn't the only formula. WebAssign's pretty good about, like, sometimes students will have different formulas, and I've seen WebAssign take like different answers. Fine, So, but this certainly would be the simplest formula. Okay, Audra, question?
Sorry, that was an accident.
Oh, okay, no problem.
Professor?
Yes, Sophie.
So I understand how you got that answer, but I don't know, going forward, how do you think is like the best way to approach trying to solve this kind of problem? Because I don't like I didn't come up with it when we were going over the problem in the beginning, and I just want to know what I can do to get that on my own.
Well, normally this one is a tough one, But now that you've seen like that, this one would be one, and that's one reason I'm doing this one, because I figure students might have a difficult time. You notice the first two sequences were easier to get the formula for,
Mm-hmm.
right?
Yeah.
This one is difficult, and this is why I did this one. I don't think you're going to see sequences more difficult than this one.
Oh, okay.
I
That's
think, because,
frustrating.
I mean, maybe when you go to graduate school, you'll see. But I took a course, a whole semester. The whole book is nothing but sequences and series. The
Oh,
whole
wow.
course. Well, or I want to say it the right way. The book I used was there's a whole book written by Conrad Knopp that's all about sequences and series.
Conrad.
Conrad Knopp, Knopp. I believe that's the author. And let's see, good question. And Renaud, well, you got to be careful, Renaud. Like -1 to the n plus 1. You know what? Hold that thought for a minute. Hold that thought for a minute. I wanna. Actually, Renaud asked a good question here. Okay, so hold on. So, all right, here's the one formula. What if I wanted to have a 2 times -1 to the n power? How would I, where n goes from 1, 2, and so forth? How could I tweak, I mean, so like the formula that you saw was this formula. This is the formula that, that's this formula. And I'm writing it below here just because I'm writing it below. Okay. But what if I didn't want a -1 to the man, hold on. What if I did not want a -1 to the n plus 1 power? Hold on. I like things to look good. No reason they shouldn't, right? Okay, so n plus 1 power. This formula, everybody's good with. But now I'm wondering, can I get away with this formula? Okay, obviously I have to put something here. What formula, what would I need to put? A minus, right. Good. Would that work? Yes. So you see, Renaud, that you have two answers that work. Two answers that work. Traditionally, people tend to like to put a plus instead of a minus. Pluses are just easier for people. So I think, how many of you did this problem would probably, if this is like the first formula, and then here's the second formula here, how many would probably do the second formula? Okay, Nathan and Michelle. And Renaud would be the first formula. So it just depends on who you are. It depends on who you are. Okay, so different formulas can generate the same sequence. Okay, are there any questions on that? Okay. Well, that being said, let me go back to the ebook for a moment. One moment. So, something of interest is whether a sequence of terms approaches a limit. This is of interest. So we have this sequence of terms that goes on forever, but does the sequence approach a limit? Well, okay, the sequence has a limit. The sequence has a limit if, and this is how you denote it, you say the limit, I mean, they have it, the limit of the sequence as n approaches infinity equals L, or the sequence goes to the limit L as n goes to infinity. Two different ways to say that a sequence has a limit. So the sequence will have a limit L if we can make the terms of the sequence as close to L as we like by taking n sufficiently large. And when the sequence has a limit, we say the sequence converges or is convergent. Otherwise, we say the sequence diverges or is divergent. Okay, so you've had you've seen convergence and divergence before in terms of improper integrals. Those improper integrals converge. An improper integral converges if it approaches a limit. Same kind of thinking for a sequence. If the sequence of numbers reaches a limit or approaches a limit, as n gets large, as n goes to infinity, the sequence has a limit. So pictorially, they have in figure 3, this is a picture of two sequences that approach the limit L. And Desmos can actually plot sequences. I'll show you how to do this in a little bit. But that's just an example of two sequences that whose limit is equal to L. Are there any questions so far? All right, well then let me go ahead and show you a few more things here. So there's a theorem. Okay, there's a theorem here that says if you have a function that has a limit as x goes to infinity, then the sequence defined by that function will also approach that limit L. So what they have here in figure 4 is they have a function, f of x, that as x gets large, the function approaches the limit L. But you see those little dots on the function? See those little dots? How many are noticing those? That the function, yeah, those dots, excellent. Those dots represent values of a sequence whose formula is f of n equals an. Okay, so if the function has a limit, the corresponding sequence defined by that function would have the same limit. I mean, it makes sense. It makes sense. Few other things. So there are limit laws for sequences. Okay, so if you have two convergent sequences, then if you were to find the limit of the sum of the two sequences, that's the first rule there, that would just be the sum of the limits of each sequence independently. The third rule says if you have the limit of a sequence C times A of n, okay, well, the constant C can be pulled out in front of the limit. Okay, the fourth rule says if you have the limit of a product of two sequences and both those sequences converge, that's just the product of the limits. So these are sort of natural intuitive rules. And notice on the right there, the limit of a constant as n goes to infinity is just a constant. So these are just natural kind of rules. Are there any questions on these limit laws? We'll look at an example. We'll look at some examples, but are there any questions? All right. Hopefully they're intuitive to you. Okay, let me show you figure 5 here. Let me show you figure 5. So figure 5, they have a picture of three sequences. Sequence AN, BN, and CN. Okay. Does it appear that the sequences AN and CN have a limit? Based on the figure there? Sure. Renaud agrees, Sophie agrees. They don't tell you what the limit is, but do the sequences AN and CN, does it look like they have the same limit? Okay, Sophie thinks so. Hold on here, let me check my little thing here. And Renaud thinks so. Yeah, well, let me ask you this. What is the sequence BN? What do you think? Do you think, I mean, the sequence BN, so we agree that the sequences AN and CN converge. They reach a limit as n gets large. Does the sequence BN also converge? Would the sequence B sub n, would it converge to the same limit as the sequences A sub n and C sub n?
Eventually.
Sorry, Samuel?
Eventually.
And why is that? All right, and Renaud says looks like it. Samuel says, so why is that? What do you notice about that sequence B sub n?
N is getting larger as we go
N
farther.
gets larger, but that's right. But as Sophie notes, the sequence B sub n is always between the sequence A sub n and C sub n, right? The sequence is always between. So the sequence B sub n has no choice but to approach the same limit as the sequences A sub n and C sub n. This is called the squeeze theorem. The squeeze theorem for sequences. How many remember the squeeze theorem from saw it in Calculus 1? Okay, Renaud recalls it. How many remember studying the squeeze theorem? Okay, Jacob and sandwich theorem, sure, absolutely. That's right, Sophie. That's right. So, indeed, this figure justifies the squeeze theorem for sequences. Okay, and the squeeze theorem for sequences says that if you have a sequence that's between two other sequences, at some point. When they say n is greater than or equal to n sub 0, that means eventually the sequence B sub n will be between sequences A sub n and C sub n. Well, if that's the case, and the limits of sequences A sub n and C sub n are both the same and equal L, that means the limit for the sequence B sub n will be forced to equal L also. Absolutely amazing result. Yes, question, Samuel.
What does that the symbol like that looks like is that just less than or equal to?
Oh, yes, yes. A sub n is less than or equal to B sub n, which is less than or equal to C sub n. So for the terms of the sequence, the middle sequence is always between the, like you got a lower sequence and a higher sequence, and the sequence B sub n is always between those two sequences. As you see here in the, maybe I could show both. See here, take a look there at the squeeze theorem and look at figure 5. Does that make reasonable sense? Okay, good, good. Samuel, how are you feeling about it? Is it okay? All right. All right. Well, we've learned some interesting things about sequences. Now let's apply them. Let's apply them to some examples. Okay. So let me go here. And are there any questions before we move on? All right. Well, then let me go ahead here. Okay, so we got here in this example, and remember, use your zoom button on the right to blow this up if you want. We want to know if the following sequences converge or diverge. And we're looking at a variety here, okay? We're looking at a variety. So I'll tell you what, let's do it one at a time. Let's do it one at a time. So in your, well, I'll let you copy it down. No, I'll let you copy this example down, okay? Let me give you a little time to copy it down, but then we'll go over them one at a time. Okay, give you another minute or two here. to copy it down. Okay, so let's take a look here at the first one. First sequence here. So well, what can we say about the terms of the sequence based on the formula? I mean, like what's the first term going to be for this sequence A? What's the first term going to be? What's it go when n is 1?
-1.
-1. Let me see. 1 times -1 to
Oh,
the
no,
power.
+1, +1.
Well, hold that thought, and I appreciate all you know, when even if an answer isn't right, I appreciate it. You know, if it's right, I appreciate it. If it's not right, because this is participation. How about this? Is this all right, Samuel? -1/3.
Did you say a to the n or
Well, what I'm doing is I'm writing the first term. The first term. So like this sequence.
oh, I thought you were asking what n like. Okay.
Well,
No.
and I'm going to start it at 1.
Okay, then
The
I
first term
was
is
saying the wrong thing then. Yeah. No,
okay. No problem. No problem. All right. What's the second term? What's the second term of the sequence? Is it positive or negative?
Positive.
Positive. Okay. What's the fraction going to be?
2/5.
2/5. I agree. Okay. What about the third term? Is the third term going to be positive or negative? It's going to be negative because you have -1. I mean, if I write out the third term here, let me just, all right, hold on. Let me just maybe put in a little more detail here. All right, Leping, sounds right, but hang on here. Hang on. So the second term, right, is 2 times -1 squared over 2 times 2 plus 1, which is 2/5. The third term is going to be 3. Let me just kind of write it here. The third term is going to be 3 times -1 cubed. I'm just following the formula here. It's like baking a cake. Times 2 times 3 plus 1. That equals -3/7. So far, terms of the sequence so far that we have are -1/3. Okay, -1/3, 2/5, -3/7. Eventually, what do you think these terms are going to start looking like? A third, 2/5, 3/7. Well, hold that thought, Renaud. One moment. If I look at this sequence and I focus on the n over 2n plus 1 part, see what I'm doing there? -1 to the nth, all that does, it goes positive, negative, which is important. But n divided by 2n plus 1, when n is large, does the 1 matter much in terms of computing the value when n is a big number? No. So all right. So let me just go to the solution here. I'll show all this is incorporated in what I'm saying here. So I wrote down the the 5 terms of the sequence. But what I'm doing is I'm gonna like just look at the absolute value of the sequence and look at that limit. The limit of the absolute value of the sequence would then be just the -1 to the nth power wouldn't be there anymore. Okay, so that would just be n over 2n plus 1, and that's going to go to 1/2. Which makes sense. How many remember working with limits back in Calculus 1? Limits of okay, you've dealt with it. So you know the trick. The tricks you learned for functions you can use for sequences. N over 2n plus 1, I can multiply by 1 over n over 1 over n because that's just really equal. That's equal to 1, right? And so I'm rewriting the sequence, but I'm not changing it. And when I do that, I get 1 over 2 plus 1 over n. But what does 1 over n do? And I'll take my email off in a minute. I mean, I'm not like looking at the email, but I don't want it to distract us. What does 1 over n do as n goes to infinity? What's that term approach? 0. So this is equal, I mean, let me just, what this equals, right? If I put in an extra step here, this equals 1 over 2 plus 0 when I take the limit, because 1 over n goes to 0, and that gives me a half. But this means then that the odd terms of the sequence approach negative a half, because that -1 to the nth power is going to be negative when you have an odd power. For even powers, for terms of the sequence a sub 2, like the even terms of the sequence a sub 2, a sub 4, a sub 6, a sub 8, and so forth, those will converge to positive a half. Because again, when n is an even number, -1 to the nth power is plus 1. So the terms of the sequence oscillate. Eventually, they're gonna approximately oscillate back and forth between negative a half and a half. They do not approach a single number, and so this sequence diverges. So I'm trying to be very sort of detailed so I can try to reach students, reach all of you, This is what, like when I'm evaluating a sequence, this is what goes on in my mind, what you're seeing here. Okay. This is like my thinking. Well, Nathan, I don't disregard the -1 to the nth power, because I mean, what I'm trying to do is I'm trying to look at this sequence. I mean, here's the sequence. Here it is. Let me write it down again. A sub n equals -1 to the nth power times n over 2n plus 1. Well, you're right. Well, now see, Nathan, you're thinking of it that way. Nathan's saying if the terms are alternating, they go positive or negative, positive, negative, positive, negative, positive, why worry about finding the limit? Well, you could have an alternating sequence whose terms get closer and closer to a limit. But what I do is I say, well, I look at n over 2n plus 1, and when n is large, that's going to be approximately, when n is large, like n over, that's going to be approximately equal to n over 2n, which is a half, because the plus 1 isn't going to matter much. It's like if you were to take 1,000 and divide it by 2 times 1,000 plus 1. Okay, what's that gonna be equal to? Almost. If you take 1,000 and divide it by 2 times 1,000 plus 1, what do you get? You get 0.4 approximately, and let me know if you're getting this. Who's getting this? 0.49975. Who's getting something like that? Let me know. Okay, Samuel is, Nathan are. So you see the one there, when n is large, okay, so I'm looking at two things here. I'm looking at two things. Think of this sequence, there's two like parts to it. one part, the negative 1 to the nth power, makes the terms of the sequence go minus, plus, minus, plus, minus, plus, and so forth. Alternating sequence. The n over 2n plus 1 part, okay, this second part, that part approaches a half, because the 1 here doesn't affect that value when n is large. It doesn't affect it too much. And so, but what I'm trying to say then is the odd terms of the sequence, where n is odd, are going to all converge to negative 1/2. Okay, because those terms are negative. The even terms of the sequence, A2, A4, A6, A8, and so forth, they're going to converge to positive 1/2, because negative 1 to an even power is positive. So the terms of the sequence don't approach a limit. They don't approach a limit. Let me show you in Desmos. So before let me just show you real quick in Desmos so you can see this. Hold on. Let me get Desmos, and then we'll come back to this, and I'll answer any questions here. Just give me one moment. Okay, let me get into Desmos. So this is, I guess this is a good problem to start with. One moment here. Okay, there's Desmos. Now, you're used to Desmos for graphing functions, but you can graph sequences. Let me show you how you do that, okay? So what you do, actually I think that's big enough, is you type in capital N equals, and what I want to do is I want to plot the first 100 terms of the sequence. So I'll say, okay, 1, 2, hold on, 1, 2, dot, 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 100. And you see there how it says n equals 100 element list? That's what you want. So it's going to plot the first 100 terms of the sequence. Now, secondly, what you have to do, and you know, you may want to plot the first 1,000 terms of the sequence. It really is up to you. Secondly, we have to type in the formula, the formula for the sequence. Well, the formula of the sequence was negative 1 to the nth power times n divided by 2 times n plus 1. Okay, I'm going to type that there. There it is. Okay. Now you notice you don't see much here on the Desmos, right? You don't see much on the Desmos. Now what you have to do is you have to put in a third command that'll plot this sequence for you. Third command is going to be left parentheses n. Remember, n is 1, 2, 3, 4 up to 100. N, comma, A sub n, big N. See on the left there how it puts a circle with dots on it? There you go. So you see on the right how it has the green dots? Now the thing is, this is not a very helpful window to see our sequence. I'm only seeing the first, how many terms am I seeing there in Desmos of the sequence? The green dots. It graphs it up to n, yeah, 10, the first 10 terms of the sequence. I'd like to see 100 terms. So what I'm going to do is I'm going to go up to the wrench here, where the graph settings, and hold on. Yeah, the wrench. And I'm going to let my x-axis, what should I let my x-axis start at? What do you think? What would make sense? yeah, maybe 0. You could do 1, but I tend to like to have the origin in my picture. So if you don't mind, I'll start the x-axis at 0. And what would I end the x-axis at? Well, or 100, sure. It's going to go up to 100. All right. So I'll put 100 here. Whoops. And a step of 1. That makes some sense. And then the y-axis, let me do the y-axis, maybe make it go from -2 to +2, something like that. Okay. And there is my sequence. So if you want to know a value of the sequence, so we learned for this sequence that the first value was hold on. The step just controls, it's the distance, it's like the scales, like the X scale I like on a TI calculator. I want like it to plot 10 points between 0 and 10, 10 points between 10 and 20, 10 points between 20 and 30. So the step is 1. All right, Sophie? Okay, good. Now what you can do is if you click on the dot here, see that? 1 -0.333. That's, oh, what's that? That means the first term of the sequence equals, well, the first term of the sequence isn't equal to -0.333. The first term of the sequence equals what? -1/3. Okay, well, rounded, that's -0.333. Now, WebAssign's not going to want, WebAssign's going to want an exact answer, right? But you got the idea. Let me see. Let me click on the second dot here. Let me see here. I guess that's up here. 2 and 0.4. So the second term of the sequence, that's what the 2 means. Second term of the sequence was 0.4. What was the second term of the sequence, class? Two-fifths. Okay, all right. So is this making sense? Is this making sense? And actually, maybe what I'll do, let me just go into Desmos. I want to change my window. I want to make the x-axis go from -1 to 1. Okay, that'll be just a little bit nicer. There we go. And then there's the first term, second term. Okay, and now let me see. Let me go out to like the 100th term here. Maybe go way out here. Maybe I'll go like this term here. Okay, that's the 94th term. That's 0.9474. Here's the 99th term, -0.4975. So do you see how Desmos is helpful for, it looks like these sequences are oscillating back and forth between -0.5 and 0.5. All right, who's comfortable with this? Please let me know if you're comfortable. Okay, Nathan's good. And all right. Sorry, I know Jacob, and I got to bring up the little people window thing so I can see who are there. And you can maybe you're not convinced that the sequence is oscillating back and forth between -0.5 and 0.5. If you want a little more convincing, just go to the wrench here and well, oh no, you can do this. You can go here and maybe make it 200. And then go to the wrench here. Hold on, let me make sure. Yeah, and then go to the wrench and have your x-axis go to 200. So plot 200 terms of the sequence. Okay. And let me just see here, one moment. Let me go out here. Let me click on like this dot here. So this was like our, hold on here. It's a little harder to, okay, that was the second term. Sorry, I'm just trying to, you got it, it's, okay, let me go out here. This is, okay, the 180th term is 0.4986, 109. So are we, how many like Desmos for sequences to help you? Is this helping you understand sequences? Good, all right, a lot of people say yes. Excellent. So now we have a graphical justification as well. Nathan, question?
Yeah, so my question initially, when you tried to find the limit, you basically separated the -1 to the n, and then found the limit as n approached infinity.
That's correct.
And I'm just wondering, why are you allowed to do that? Because I remember that 1 raised to the infinity power is indeterminate.
Well, but -1 raised to the, so you're talking -1 to the nth power there?
Yeah.
Keep in mind, it is -1. It's not like negative point, it's, it's not like you're looking at something, I want to say this the right way. Hold on. Good question. So you're thinking of L'Hopital's rule here. Those indeterminate forms, section 4.5. And you're thinking of something like, all right, let me go to the whiteboard here. What you're thinking of, it's not, so like if you are finding, I'm going to get my, hold on, let me get my mail off here. Sorry, I don't want any distractions. All right, so if you look at the limit, for instance, as, got to be a little careful here. Let's say as n approaches infinity of 1 plus the sine of n. Got to be careful here. No, that's not what I want. That's not what I want. One moment here. One moment. I have to think of an example here. Okay. Okay, so if you were to have the limit as n goes to infinity of something like n to the 1 over n power. This is like an indeterminate form, 1 to infinity. Or I'm sorry. No, that's not exactly what you're looking at. That's not exactly. No, I got something. No, let me hold on. No, let's do it again. Let's take this. The limit as n goes to infinity of 1 plus 1 over n raised to the nth power. Now that's an indeterminate form, right? That's like, as n gets large, that's like 1 to the infinity power, right? And you're saying, hey, why can you, you're like saying, let's compare it to this, right? Well, in fact, this here, this below, this -1 to the nth power, the -1, you're not looking at -1 to the nth power. I mean, you're not like, I want to say this the right way. You're not looking at -1 to the nth power and taking the limit. You're not doing that at all. You're not doing that at all. What you're doing is this. Let me go back to the solution here. All you're doing is all you're doing is you're saying that for this sequence, this part of the sequence, n over n plus 1, that's going to approach a half when n is large. The other part of the sequence, which is -1 to the nth power, all that's going to do is give you plus or minus, or minus plus, minus plus, minus plus. So that's why some of the terms of the sequence go to -1/2, converge to -1/2. Other terms of the sequence converge to +1/2. But since some of the terms of the sequence approach one limit and other terms of the sequence approach another limit, -1/2 and 1/2, the sequence can't converge. It doesn't approach a single limit. That's how you have to, that's how you think about it.
I understand that. I guess my follow-up question is just going to be, when we try to find the limit of sequences, can we just like separate any like factor that might change the sign?
You could. You could. You could.
Okay.
Now this, but you know, you understand what I'm not saying. I'm not saying that. Right? You could. You could. Yep. Let's tell you what. Let's look at a few others, and we'll. Good questions. Good questions. No, Leping, not all alternate sequences diverge. As a matter of fact, let's look at this sequence here, sequence B. Now, you have this 0.2 to the nth power. So that's like 0.2 to the nth power, right? It's like 1/5 to the nth power. As n gets large, what would 1/5 to the nth power approach? I mean, if you took a fifth times 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 a fifth, it's going to go to 0, right? So what is this sequence? What is this sequence? I mean, this isn't an alternating sequence, but what is this sequence? You think this sequence in B converges? Yeah, to 3. That's right. Good, Renat. Good. And here's like the work, the write-up of the solution here. So I'm trying to be sort of very almost conversational in terms of what I'm writing down here to help you give an intuitive feel for these sequences. So I write down the first 3 terms. I compute the first 3 terms of the sequence. First 3 terms here. And it looks like the sequence is approaching 3. Okay, it looks like it, right? I mean, 2.992, that's pretty close to 3. Well, if I take the limit of the nth term of the sequence, I get 3. And so the sequence converges to 3. Okay, let me know if you have any questions. I'll give you a moment to copy that down. Okay, are there any questions before we move to the third one? Because I want to, of course, I'm going to let you do some classwork on this. But, all right, well then let's go to the next one. Here we have the tangent of an angle. The angle is 2n pi over 1 plus 8n. So I'm looking at the angle. I'm looking at this angle. 2n pi over 1 plus 8n. Now, as n gets large, what does that angle approach a number? Okay, good, Nathan. Nathan says 2 pi over 8. That's right, because the 1 here, when n is large, that 1 isn't going to affect the angle very much. It's going to be very, very tiny. Okay, so that angle approaches 2 pi over 8. Now, what's another way of saying 2 pi over 8? Oh, pi over 4. Okay, so what do you think this sequence of terms is going to approach then? The angle approaches pi over 4 when as n goes to infinity. The tangent of pi over 4, that's right, Renat. And what is the tangent of pi over 4? What is the tangent of 45 degrees? Good, good Leping, good Nathan, it's 1. So this sequence converges to 1. Okay, and here's the workout on it. So this is writing out a little more formally. I don't, so I mean, these sequence problems, I mean, like you could, for instance, how many might go to Desmos and plot that sequence to see what happens? Okay, Marcus would. Okay, and that's okay. There are different ways to do it. Different ways to do it. That's okay. So, okay. So what I do, if I'm being formal about it, I'm going to multiply by 1 over n, okay, on the top and the bottom, so I can rewrite that angle in a little bit easier form to analyze. I mean, it's okay. Hey, we don't need to do that. We know that but I'm just trying to be formal about it. Clearly, the 1 over n approaches 0 here as n goes to infinity, giving you 2 pi over 8. You notice that I write equals tangent of 2 pi over 8. After I take the limit, I get equals tangent of 2 pi over 8. But there's no limit sign anymore, right? Because I took the limit. So when I write my work, I try to be very careful how I write it, very precise. Okay, are there any questions before we go to the next one? Okay, well then let's move on. Okay, now D, for D, the formula is 4n minus 1 factorial over 4n plus 1 factorial. How many have seen factorials before? The exclamation mark means, okay, Renaud's seen it. And who else here? A number of you. I mean, if so like 0 factorial is defined to be 1. 1 factorial is defined to be 1. 2 factorial is equal to 1 times 2. Okay. 3 factorial is 1 times 2 times 3, or 3 times 2 times 1. 4 factorial is 1 times 2 times 3 times 4, and so forth. How many, you must have seen this somewhere. How many remember that from their, okay, Jacob remembers seeing that. You're welcome, Nathan. Gloria, Sophie, and Jacob. All right, all right. So, well, so what we have to do now, this one here would be hard to do in Desmos, okay, because it just would be difficult. So we have to really mathematically look at it. So let me go to the solution. Okay, so what I do is I just, you know, again, a little bit conversational here. I write down the first couple terms of the sequence. 3 factorial equals 6. 5 factorial is equal to 120. 7 factorial is equal to 5,040. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. You know, 9 factorial is actually equal to 362,880. And, you know, but what happens is, you see, is the computers can't compute. When the factorials get too large, they can't compute it. So we got to do this algebraically. So what I do is I want to do a simplification. I'm going to leave the numerator alone, but I'm going to write out the denominator. The denominator is clear. The denominator is clearly bigger than the numerator because 4n plus 1 is larger than 4n minus 1. So 4n plus 1 factorial. Okay, I mean, just like, you know, again, if I have like, if I have, you know, if I have 5 factorial, that equals, let me just, hold on here. Okay, so we're looking at this here, and we write 4n plus 1 factorial, we write it out. So again, you know, like I always think of a simple case. 5 factorial is 5 times 4 times 3 times 2 times 1, right? So 4n plus 1 factorial would be 4n plus 1 times 4n, which is 1 less, and then times 4n minus 1 times 4n minus 2, all the way down to 321. But the 4n minus 1 times 4n minus 2 times all the way down to 3 times 2 times 1, that just equals 4n minus 1 factorial, right? That's what that equals. And we can simplify that then, and that's going to give us 1 over 4n plus 1 times 4n. Well, as n goes to infinity, that numerator gets larger, and we get a 0 for the limit. And so the sequence converges to 0. Absolutely amazing. So I'm trying to do a variety of different problems with you. so that you'll be, you'll be in good shape for the homework for section 8.1. Are there any questions at all? Okay, then let's move on to the next one. Let's move on to the next one. So here now, for E, okay, look at this. 2 times the square root of n times the sine of pi divided by the square root of n. Okay, now we could try Desmos, but Desmos, the thing is, sequences, if they converge, sometimes the limit is not something. WebAssign and I want an exact answer. Desmos will give you, will help you, but to tell you pretty close to what the limit should be, but it may not give you the exact answer. Well, it wouldn't give you the exact answer, right? And based on a decimal, you still might have trouble figuring out the exact answer. So, but I look at this. I look at this here, and when we have the square root of n, as n gets large, what does the square root of n approach as n gets large? What's the square root of n go to? It goes to infinity, right? N goes to, yeah, so you got something going to infinity. And then the sine of pi over root n, that's going to approach the sine of what as n gets large? What's pi over square root of n? What's that angle approach as n gets large? 0. That's right, Nathan. And what's the sine of 0? 0. Okay, good. So here now you have, in this sequence, you have a product of 2 terms. One's approaching infinity, one's approaching 0. What did you learn about infinity times 0 from L'Hopital's rule? What kind of form is that? Infinity times 0.
Indeterminate rule.
That's right, Samuel. It's an indeterminate form. So we're going to utilize L'Hopital's rule for this to help us. So we're going to look at the function 2 times the square root of x times the sine of pi over square root of x and see what that limit is. And based off of that, we can learn about what our sequence will approach. Okay, so let me show you how that works. Okay, so here, this is section 4.5, right? So again, you have an indeterminate form of some infinity times 0, but to use L'Hopital's rule, we need either, what are the forms that'll work for L'Hopital's rule? Do you remember?
G prime of x over h prime of x.
Well, for L'Hopital's rule, well, 0 over 0 or plus or minus infinity or plus or minus infinity are the indeterminate forms that we're gonna use to do the L'Hopital's rule. So what I have to do is I have to rewrite my function this way. Okay, I rewrite the function like this. And so the sign, you have basically let me just do this here. Hold on. So I think you're okay going to here, right? And 1 over x to the half, as x gets large, what does 1 over x to the half approach? What does 1 over the square root of x approach as x goes to infinity? It goes to goes to 0. That's right. Square root of x gets large with x. So 1 over square root of x will go to 0. And the sign of pi over x to the root half, that's going to approach the sign of 0, which is 0. So you get this indeterminate form. And that, therefore, you can use L'Hopital's rule. And you take the derivative of the top function and the bottom function, which I did here. And then, you know, you do a little simplification. And therefore, you'll see that the limit equals 2 pi. Therefore, our sequence converges to 2 pi as well. So you see, Desmos might, like if you were to go out like 1,000 terms, Desmos might, you know, you might click on one of those dots, say the 990th term, and it might say like 2 point, let me see here, one moment. It might say like the 990th term might be equal to 6.245, something like that. Well, you know, Web of Science is not going to accept that answer, right? It wants a simplified radical form answer, an exact answer, unless you're told otherwise, unless it says use a decimal, it wants an exact answer. So 2 pi, and this is how you would get it, you see? All right, are there any questions on that? We have one more to go, and then I'll be able to let you work a little bit. How many are finding these sequences to be pretty interesting? How many of you are liking section 8.1? Okay, quite a few people here. Good, yeah, it's fun, right? It's fun. All right, may I go to the last problem? Okay, Jacob's good. Okay, Nicole's good, all right. Sophie, the textbook did mention a Fibonacci sequence. We're going to keep Fibonacci sequences are famous, but we're going to keep it simple for, well, hold that thought for just a minute. One moment here. Yeah, we're going to keep things simple right now. All right, sounds good. Sounds good. Okay. Okay, final sequence. Final sequence. -3 to the nth power over n factorial. Okay. All right, Samuel. So Sophie and Samuel have experience Fibonacci sequences in various ways. All right, good. Samuel says there's a song that's based on the Fibonacci sequence. Which song, Samuel? Lateralis. Okay. All right. Maybe I'll have to check that out this weekend. All right. All right. Well, you know we haven't used the squeeze theorem yet. This here, you know, this here, last sequence is a tough sequence. We're going to have to use the squeeze theorem on it. So here we go. What I do with the squeeze theorem is I don't want to worry about, well, I want to look at the absolute value of the sequence. Okay, the absolute value of the sequence would be 3n over n factorial. Now the question is, if I can write this right here, if the limit as n goes to infinity of the absolute value of a sequence is equal to 0, then the limit as n goes to infinity of the sequence also equals 0. So the point is, and I think that would make pretty good sense, right? So if you have a sequence that's oscillating or alternating, positive, negative, positive, negative, positive, negative, but the terms get smaller and smaller over time, that sequence is going to go to approach a limit of 0. So certainly, and this is actually a theorem, what I wrote at the top, it's theorem 4. If we can show the absolute value of the terms of the sequence approach 0, then the sequence itself would approach 0. It doesn't matter whether the terms are doing positive or negative, they're alternating, they're all getting smaller. So what I do is, for n greater than 2, okay, the absolute value of the sequence, I want to say this the right way. If I write out, like, I want to say this the right way. If I take like if I take like 3 squared over 2 factorial, that equals 3 squared over 1 times 2, which is 3 over 1 times 3 over 2. If I take 3 cubed over 3 factorial, remember the formula is 3n over n factorial. 3 cubed over 3 factorial is 3 times 3 times 3 all over 1 times 2 times 3. And so you see you can separate it out. Okay, so let me just see here. Yeah, so the general pattern is you can expand 3n over n factorial like this. But we note that all of these terms here, all of the, well, I want to say this the right way. These terms here are going to be less than 1. The product of those terms there, let me phrase it the right way. The product of these terms here is less than 1. That's why you can put the less than or equal to. So you have the 3 over 1, the 3 over 2, 3 over 1, 3 over 2. You have the 3n, and then this part here is less than or equal to 1. So that's why you have the less than or equal to. And this on the right equals 27 over n. So the squeeze theorem, you know, this is just a way to apply it, 27 over n. So this means then that for n greater than 2, the absolute value of our sequence is always less than or equal to 27 divided by 2n. Okay. And if you take the limit of 27 over 2n as n goes to infinity, that equals 0. And so therefore, by the squeeze theorem, the absolute value of our sequence also has to approach 0 as n goes to infinity as well. Okay, so since the absolute value of our sequence approaches 0, that means then as n goes to infinity, that means our sequence approaches 0 as well. And so our sequence converges to 0. In other words, n factorial, the denominator, the factorial grows more quickly than the exponential term on the top. You've been kind of taught that exponential terms are like maybe the fastest growth, but the factorials grow faster. So, you know, this is kind of a tough one, but this is how you would do it. And I thought it was important. You're not going to have probably a whole lot of problems dealing with the squeeze theorem. You'll have some, but I thought it was good that you see this example. Just to, and they do another one, example 9 in the book, just so that, you know, you have an example of it. Are there any questions? Samuel? Yep.
Wait, so it's convergent towards 0?
It is. It is. This sequence converges to 0. That's correct. All right. And are there any other good questions? Okay, I'll stop the recording.